Now we all know that coefficient of friction is not on the course. It got removed. We all know that. Some teachers still did that. They could have done it as part of your option, but you will not get ones which have the coefficient of friction in there. That's good. That's okay. We're allowed to do that. It's good. It's good for it. It's a good topic. But just be aware that it is not on there anymore. So they made some room to do that. Statistics, which you all love. Yes. Coefficient of friction. Okay, so what they're going to do is they'll say, we've got some crate being pushed along the ground, something like that, and they'll say the sum of the resistive forces is 15 newtons. Okay, or it's being pushed up a plane, whatever it is. It'll just say the sum of all the resistive forces is whatever, 15 newtons against the motion of the whatever it is you're pushing. Okay, so that's how it goes now. So it makes life quite easy, really, when you think about it, for those types of questions. So, which is a little bit annoying, because it was really good. All right. So, kilogram weight. I don't think VCAA will give you things in kilogram weight. The only difference is you have to multiply that value by G and you get newtons. So, that's all you have to do. Some conversions if you've got to, that are there in the notes. We have weight forces, force due to gravity, normal reaction force. So, you know, why isn't my Wacom screen here that I'm writing on lifting off the ground? Why is it this screen isn't lifting off the ground? It's because there's a normal reaction, isn't there? Which is equal and opposite to the mass times gravity going down, and the normal reaction is exactly opposite, so it's not moving at all. Okay? So just with that, I'd just like you to pay a little bit more attention to perhaps your diagram. Remember, in specialist maths, we consider it a point particle. So if you do draw yourself a little box or a circular thing, a circle or whatever, just put the forces coming out of the center of the object. We do not have anything about, you know, at the surface like physics. So it's very simple, point particle. Just put a dot if you want for where it is. But please put it out of the center. Now, I just want you to pay a little bit of attention to the length of the vectors that you make. It's not really to scale, is it? So if I was told to draw a force vector diagram, you'd expect not to draw something like that. All right, I have exaggerated it a bit, but if that was my Wacom screen, it would be levitating up, wouldn't it? And continuing going and hit the roof. Okay, so what just I'd like you to do is just pay a little bit more attention to the length that you make, and they should be equal and opposite. Okay? We do not know actually what the lengths will be until we calculate it. So don't worry about that, just as long as you've got them roughly in. Now, my definition of rough to your definition of rough could be quite different. Is that correct? So put it about the length it should be. Okay? All right? And then if you've got to do that, it's normally worth 1 mark or sometimes 2 depending on the number of forces. Previously it was probably 2 for some questions, but normally it's 1 mark. It's one of the easiest marks you can get, so don't sort of, you know, miss it. So if we were going to do it on here, let's say that we've got some force here. If I'm going to do the normal reaction, now I do not draw these things as straight lines because they're not actual forces, are they? So if I said draw a force vector diagram of everything acting on that, we'd say, well, there's my normal reaction there. I do not draw these. What are those? What are they called? What are those two parts called? Components. They're not actual forces, are they? So the forces we have would be the normal reaction, and the normal reaction is equal and opposite to that component of the weight force going down. Okay? And if this was being pulled up the plane, and we're told something about the frictional forces, let's say we're told it was moving up the plane, and it's on a rough surface, and we're told that the frictional forces were, say, I don't know, 3 newtons, then we're not going to draw it like that, are we? Because that says it's going to be going down the plane. Okay, so just put it roughly in about, so if this is a force being applied, we'll call it P, we're not going to put a force like that length. We're going to put something which obviously has to be less than F. And we might just put it there and say that's 3 newtons, okay? All right? So just put them in proportion. Okay, enough said about that. Okay, we've got our normal reaction there, etc. And we've got our frictional force, so it just opposes motion. Okay, we could sometimes get the motion wrong whether it goes up or down a plane, can't we? We might predict it wrong when we've got two things. So just be aware. So if you've got a plane and or two planes, two objects on either side, and we predict that this one's going to go down and that one's going to go up, and we get it wrong, the only thing that's going to happen is our acceleration would be negative. Yep. And we see first two things we're going to check about that. Did I make a mistake with my calculation? No, perfectly correct. It just means you predicted which object would move in the wrong direction to start with. So no issues with that. Tension. So we assume that the strings have no weight, they're inextensible, they do not stretch, okay? And the tension is equal and opposite in between the two bodies, which are here, okay? Okay. If it goes over a pulley, it is quite possible to have on one side that the tension on one side is twice that on the other side. So there's some friction around the pulley. So that is possible, and they'll describe it to you, okay? Or it's like that. Now this is a common multiple choice question. So please don't get it wrong. The wrong answer is actually there. All right. So let's just think about that. All right, which one do you want to be heavier? W1 or W2? Right, because it's lower. So we'll say W1 is greater than W2. Yep. So we expect that the things are going to go down, don't we? Yeah. We expect that it's going to move this way, correct? Gravity acts downwards, doesn't it? Yeah. So in this case, when this one goes down, this one actually goes up, doesn't it? And one of the mistakes is that they assume that the forces, they're both moving downwards on either side. So that's one of the mistakes you forget. So it goes plus in that direction, and it would go plus in that direction. Okay, so just be aware of that. So if we're resolving vertically for this one, it would be W1 minus T equals mass times acceleration, if it was accelerated. And this one would be T minus W2 equals the mass times acceleration of that body. Okay, so don't get that one mixed up. Multiple choice common. All right, so we've got that. So you guys like these? This sort of stuff? It goes on about drawing all the forces. I've mentioned that already. And then we've got Newton's law of motion, which is there. Okay. Some of the forces or some of the resultant forces which are there. Okay, so I think we should just jump into a couple of questions. We've talked about that enough. All right, so I'm just going to have a quick look at what we've got here. Okay, 65 is the one we're going to do. Okay, so a body of mass 18 kilograms is being pulled along a rough horizontal surface by a force of magnitude 10 newtons acting at an angle of 30 degrees to the horizontal. If the body is moving with constant velocity, okay, so you see constant velocity. What goes in your mind there? Yeah, the acceleration is 0. So when we come to do the formula sum of the forces equals mass times acceleration, we're just going to say the sum of the forces equals 0. So someone could say it's in equilibrium, couldn't they? Yep. All right. And the downwards gravity force, G, is 9.8 meters per second squared. Now, we use 9.8. It's on the front cover. Do not use it. All right, so let's read what we've got to do. The resistive force P newtons acting horizontally against the motion. So we've got to find these. And the normal reaction acting perpendicular to the plane. So we've got a body of mass 18 being pulled along a rough horizontal surface by a force of 10 newtons at an angle of 30 degrees. Okay, so there's our plane, which is at 30 degrees. We've got our body, which is here, can just be a block. And we have a force which is acting on that body, which is at magnitude, rough horizontal surface. Sorry, I read that incorrectly. That's my fault. jumping into the more trickier one to start with. Okay, so it sits on a horizontal surface. There's our body. Okay, and it's being pulled by a force at an angle of 30 degrees. 30 degrees. There it is. Okay, and we have a weight force, and that was 18 kilograms. So it's 18G. And we have a normal reaction, equal and opposite in length. Doesn't mean my scales are correct. We have a horizontal force of magnitude 10 newtons there. Okay, it's our normal reaction. And what else do we have? Frictional force. And what do we know about the frictional force? Anything? Yep, the resistive force P. So P is going to be there. And the only thing we know about that is that resistive force must be shorter than this length that we've indicated here. Okay? Alright, so there's our P. Alright, so what are we going to do? What are we going to do? Part A. Got to work out that resistive force, don't we? Now, with that, what did we say it was in? Equilibrium. So, going back to what I said, no one said anything. I was wondering to see what you would say if it's in equilibrium. Is it moving? Yeah, it's moving. But that force has to be the same length, doesn't it? Otherwise it would be speeding up. Yeah? It's moving with constant velocity. And if these forces, this horizontal component here, force is not the same, equal and opposite of that, we're going to have an overall force acting either slowing it down or speeding it up, aren't we? So they have to be the same length across the components. You agree with that? Yep. Alright. You guys must be tired. So, we've got the sum of the forces equals 0. We are going to resolve horizontally. So I suggest what you do is you say something like RH, resolve horizontally. Okay, we've got our rule. So, now the last thing we've got to do is say, what are we going to do? We're going to put some directions on there, aren't we? So I'm saying upwards is positive and to the right is positive. So I'm going to do the positive forces first. So 10 minus P equals, sum of the forces is 0, so that's 0, so P equals 10. And it's 10 what? Oh, sorry. I'll just go back. I think I really needed that short break, didn't I, myself? So we've got the horizontal one, so it's P cos 30 equals 0. So P will be 10 on cos 30. Ah, all right. Do you know in your exam that you guys must make me nervous? No. Sometimes you do not concentrate very well. Is that correct? And sometimes I love it how we have an exam and we do not talk. Yep. So we can put our full attention on it. All right. So if you have a moment, just take a moment out of your exam. Take in your clear bottle of water. This isn't clear. You're going to take in a clear bottle, rip off the label. Okay, have a drink, have a break, come back, go on to another question if that's what the case is, come back to the question that you're working on, and you start again. Okay, so let's just go over that one more time. So we're going to resolve horizontally. So 10 cos 30, so we want this component force going across there, so 10 cos 30 minus P would be equal to 0. Now I've got a pattern here. I'm not just going to say, we all know that P equals 10 cos 30, correct? So I'm going to set up for every time I do one of these questions the same thing. Sometimes I might write one extra line, sometimes I might not, okay? So if we had this body was accelerating, I'd be putting MA on the other side, wouldn't I? Instead of 0. So I'm just doing the same method. So every time I do one of these questions, I'm going to do the same method. If we only do one method for every question, we shouldn't get confused. Is that correct? Yep. All right. So P, and what's cos 30? Cos 30? Root 3 on 2. So that's going to be 5 root 3. Is that correct? Yep. Don't forget your newtons. Part B. Let's do part B over here. The normal reaction. In this case, we are going to resolve what? vertically. So we're going to do the positive forces first. We have the normal reaction. And we're going to add to that the vertical component of the 10 newtons. So that will be plus 10 sine 30. And in the other direction, we are going to subtract our 18g. And again, that will equal 0 because it's not moving off the surface, is it? So we're going to find that n equals 18g minus 10 times sine 30 is a half, which will be, now how do we leave our answer? Do we leave it as 18g minus 5 newtons? Do we have to, alright, the question is, do I have to put in g equals 9.8? Now, 18 times 9.8, that's not very nice, is it? You could. So you could go through and say, well, look, it's, or you go 4.9 or 49 on whatever. So the suggestion was there, you can make it 98 on 10 or 49 on 5. And then you're going to have to multiply it out, aren't you? So you're going to have to go 18 times 49 on 5, etc. and multiply it out and then subtract your 5. Okay? So a little bit annoying. So I'd probably say if it was in the exam, it would be a much nicer number than that to do that. So in your answers, they've left it like that. So if they really did want that, they'd say up here in terms of G. You agree with me on that? So there's, in a tech-free exam, they're not going to make you do something which is pretty ugly or take quite a while because it's just an arithmetic thing. All right? So what I would really do up here is I would get rid of that and say in terms of G. Okay? Is what I'd do for the second one. Okay? So we just add that in there, which means this is our answer here. Okay? That makes sense to you? They do that sometimes. So if they don't say that and it's a CAS exam, I'd be multiplying it out. Okay. Who likes this stuff? Yeah? Okay. So this is where I said that one method fits all. If we can do that, it would be good, wouldn't it? Okay. Okay, let's have a look at 66. A box of mass 10 kilograms lies on the horizontal floor of a lift, which is accelerating upwards at 2 meters per second. Okay, so we've got a box, got our lift, got a box on the lift, and it's accelerating upwards at 2 meters per second squared. And the acceleration due to gravity is 9.8. Find the force in newtons of the lift of the floor on the box. So what's that we're finding? So since it's going upwards, we might as well make that positive going upwards. Is that correct? The box is 10G. Yep. It's our weight force. And then we're going to get this normal reaction. Correct? Okay. Now, we are going to use the sum of the forces equals MA. Yep. So, we are going to resolve vertically, RV. Do the positive ones first. So N minus 10G equals the mass, which is 10, times the acceleration, which is 2. And we'll find that N equals 10 times G, which is 98. Nice number to work out. Okay. Plus 20, which is 118. Now, that's our force. Is it not? Okay. Part B to that question might be, how much is what is our perceived mass of the box now? Be a nice little addition. So just divide that by 9.8. Yes? Yep. So, we all know that when we go up in the lift or we go down, we get different sensations because we feel either heavier or lighter, don't we? Okay, so lift questions like that are quite nice to have a go at. Now, did you notice that I did the same setup for this question as the last? Okay, so even though up here we could have saved the line, here I could have said the answer is, I've got one method that fits all questions. Okay, so just set it up like that. Okay, 67. Have a look at 67. Okay, a particle of mass 25 kilo. Just one thing with the last question. Just in the answers, just on the diagram, someone's put 5 meters per second squared. Okay, just be aware of that. It's 2, so they've just written the wrong thing, but the calculation's correct. Someone's just typed it in, just handwritten it incorrectly on that one. So just be aware of the answer there. It's just on the diagram only, the rest is correct. So this time we've got a particle of mass 25 kilograms, which rests on a rough plane inclined at 30 degrees to the horizontal. A force of P parallel to the plane is acting on the particle and stopping the particle from sliding down. Find the minimum value of this force which will prevent the particle from sliding down the plane. What will happen if the magnitude of P is greater than this minimum value? Okay. Alright, so we had a particle of mass 25 kilograms resting on a plane of angle 30 degrees. And there's our particle. Okay. And it is 25 kilograms, so I'm going to call that 25G. Okay. A force P parallel to the plane is acting on the particle and is stopping the particle from sliding down the plane. So we've got this P. Okay, stopping it from sliding down the plane. So what do we notice so far? Anything else? What other forces do we have on there? Sorry? The normal force. So if I did some dashes down there, we would say the normal force would be about that length. Yep. Okay. So, anything else? Friction. Is there friction? Yes, it says there's a rough plane. So it's stopping it from sliding down the plane. So which way is friction going to act in? So, well, let's just read it again. A mass of 25 kg rests on a rough inclined plane at an angle of 30 degrees to the horizontal. A force P parallel to the plane is acting on the particle and stopping the particle from sliding down the plane. So it's not going down the plane, is it? Sorry, what? Friction's going up. So the motion it's stopping it from sliding down the plane. Yep. So the friction will act opposite to that, so the friction is going to be acting upwards. Is that right? Okay. Are we all good with that? Now, just thinking about the question, what should we do? Now, do we have to add the frictional force in here? Because it's stationary. It's not moving. So even though it's rough, it's not there. It says P is stopping it from moving. So what is it? Yeah, they probably shouldn't have said that. So they don't want this force in there. So it's at rest. So sum of the forces is 0. So I read this question earlier and I didn't really see our friction was entered in there. So it's really a little bit of a furphy in that. So it's at rest, so it's not moving. Now, what's this bit about? It's part of it is the force P is stopping it sliding down the plane. So what's that sort of saying? Alright, let's make something up here. What have we got we can use? Our box. Let's use our box. We've got that there. There's our box. What have we got we can use over here? Maybe my calculator, not the other one. Some point in time, it's going to start sliding, isn't it? Okay. So let's say that's 30 degrees when it's just about to slide. Okay, right there. We'll say that's 30 degrees. That's our thing. I'm now going to put a force that will stop it from sliding. All right, so we've really got that action going on there. All right, so we're happy with that? So this is just going to prevent it from moving down. Yep, we all happy? All right. So that's the situation. I think, so what's the force that's really going to stop it? Sum of the forces is 0. So if we resolve, really we've got this diagram here. Yep. So we're going to say that resolve parallel to the plane. So resolve parallel to the plane. And what are we going to get? Now just on the diagram that you have in the answers, just want to show you something in that. And I don't want you to do this. So we'll just come and find it. Lovely, lots of answers there. Let's just go a little bit quicker. There you go, 63. What are we up to? 67. Okay, here we go, 67. Now, just with this. This is how you might work things out, is that correct? So, if you were asked to do someone's done this just as a calculation thing, all right? They've looked at the components of this one, and it doesn't quite line up, and they've said, we've got our two components. We've got this part, which is here, and this part, which is here, they've put down there. So they're just looking at it as working it out. They are not forces. So it's just a calculation thing. It's not a force vector diagram. We happy with that? So they've just done it as how they would calculate it. If it is not moving, they've tried to make that this length here is the same as that. So they've just tried to show you that the lengths are the same. All right. So this is not a force vector diagram. It's just something that someone's drawn to help calculate the components. All right. So components of our weight force 25G. So it's not a force vector diagram. So if you wanted a force vector diagram, you do not put this one in there and you do not put that one in there. Okay, we happy with that? All right, it's just for calculations only. So just make that quite clear when you come to look at that question that that is not the case. I normally do not draw them in, just in case it is one of those questions. So you know how you get into habits, you put them in. Now, some physics guys might put them in to work out whether something's going to go up the plane or down the plane. Am I correct there? You look at those components, you say, is it going to go up or down? You calculate those things and see which one's larger, and it'll either go up or the plane. Is P larger? Or let's say it was moving in one direction. We'd then say, is the P larger or is the 25 G sine 30 larger? Okay, so for physics, you might do it that way. All right, let's get back to it, and let's just resolve. All right, so we're going to resolve parallel to the plane, just the two lines. And we'll say positive is upwards like that. Yep. So we're going to go P minus this component which is going down in this direction. So it's going to be 25. This angle is 30 degrees, the same as the plane. So 25 G sine 30, which is in there. And then we're going to say that will equal 0 because it's not moving. Therefore P and sine 30 is half. So we've got 25 on 2 G. And we'll leave it in terms of G, I believe. Okay. All right. So we're all happy. Now, part B. What will happen if the magnitude of P is greater than this minimum value? It'll move up the plane. So, P is greater than 25 on 2 G. It's going to move up the plane. because the force will be larger. All right, so let's grab our little box and the calculator again, whatever I put with that, whatever, over here. Okay, so here we have our plane, and we're now going to, that's stopping it from sliding, so we're now going to apply a little force. It will move up, won't it? So if I let it go, it slides down, but I've now put in just enough to stop it, increase it, goes up the plane. I think I'd reword that question slightly for next time we do it. Yes?
I know the coefficient of friction is not in the code.
Yes?
But can't you consider it when it's sliding down?
You can, and this is not the intent. Yeah. They shouldn't have the word rough on that. Yeah. It wasn't supposed to be there. If it was rough, yeah. So what they'd say in the VCAA exam, they'd say the sum of the resistive forces is...
Yeah, and then you have the result.
And then you have it. So what you might say is the sum of the resistors. So really, to do this, we'd say it's just sitting on a plane. Okay? Okay? And I'd actually go here to say we should really put smooth. Okay? Because that would make more sense. Okay? So we do that. Rewrite the question. I'd rewrite the question. I'd do that. Otherwise, they'd have to add in that the sum of the resistive forces is this. So what they're assuming is that P, in that question as it was written before, overcomes, also includes the frictional forces. So I think if we made that smooth, it would be a bit better. You agree? Yep. All right. Now, let's go on. So 68 is a Lami's question. So we've already covered Lami's theorem. So it's just the same thing. It's a Lami's question. We've got a nice little worked example there. And you notice how it's all set up here with the dashes and all that. That is a much better representation if you're actually going to show that. They are, you must do them dashed. Do not do them as solid lines because they're not physical forces. Okay, they are components of the weight first acting parallel and perpendicular to the plane. So who's been drawing them as solid before? Yep, do not draw them solid. Because of force vector diagram, they are not actual forces. You understand that now? Yep. So that'd be a lovely diagram there. And again, if you have a look, the only thing that I would write down is, and we just have a look at the directions, I would write this, sum of the forces MA, or sum of the resultant forces R. I'd make sure I put a plus and plus on there, and therefore this is why they've done the mg first, okay, because they've said positive is going down. All right, so you make your directions and then you stick with them. Okay. All right, and it goes from there. The diagram doesn't look very nice. Something's happened with that. Okay, so you get rid of that, I think, and you get rid of that, and I'm not quite sure why this is there. So something's happened with that diagram. Okay. So I'll get them to fix that one up. Alright, so you've got some diagrams there. CAS, use your CAS. That's a class pad image. So solve your equations if you have to. Oh, one thing we should say, when you go to your CAS, would you just type that in as it is like they've done here? Or would you simplify it first? What would you guys do? Simplify it. Just make sure you don't make a mistake. It takes a little bit of effort to put in these. Well, we have to put in the cos 40, don't we? But the sine 30 is half. We'll remember that. Not too much. But if you're worried about, making some sort of mistake, just put in the angles. What's the only other thing you've got to make sure you do? Right, it's degrees. So you've got to have your degrees, mate. Now with that, I think it was this for the TI people. With that, the class pad's nice because degree is down the bottom. You got your touch screen. With the I can't show you on the screen here, but with your TI, if you take your touch pad up and you press the degrees, it will click from degrees, radians, degrees, radians. Gradians has been removed to do that now. Yes? No, it works on the old one. Works on the old one. Yeah, pretty sure it works on the old one there. It was in the last update, I think, for the old one. Now those people with the old one, that was the last update. It's now gone. All right. So we have another lift question there, or a rock climber. No, sorry, the rock climber one here. 71's the rock climber, which is there. And it's a bit like the lift question. So we want to have a go at the rock climber? Yes? Yes or no? Because the one that I had next listed was the one with the pulley over the top. So, which one do you want to do? Pulley. Okay, pulley it is. So 73. So you had another one which was fully worked for you. So we'll go to 73. And let's go through and work this one out. So we've got a mass of 1.5 kilograms is connected to a mass of 2 kilograms by a light inelastic string which passes over a smooth pulley. Important to know that. So we've got our two masses. Which mass is going to move downwards? The 2. So let's draw up our diagram. So we've got our 1.5 on this side. So 1.5 G. We've got our 2 on this side. So because it goes downwards, I'm going to put it a bit lower just to sort of say it goes that way. Okay. Okay, so the motion's going to be like that you agreed. So we're going to call positive downwards. And therefore this one has no choice. It's like having a big bully, you know. He says, oh, I'm bigger than you, I'm stronger than you. And he comes over and says, oh, you got your desk up. So if I said to this guy over here, I said, I'm the big bully. Wherever I go, I'm twice your weight. You're just going to come with me no matter what happens, correct? No matter how he pulls, he's going to eventually come because he has no choice. He's got no grip with his feet because he's sitting down. So I'm going to pull you up. So same with this. This 2 kilograms is the big bully. This 1.5 has no choice. It just has to follow because we're in a string that does not spring out or anything like that. It's inextensible. Right? So he's just got to go with the flow. So 1.5 goes up. Do not make that mistake. The answer in multiple choice is there. Now the other thing, it's a smooth pulley. The other thing we have is tension in the string. Is that correct? And it will be equal and opposite in the directions that they occur. All right. So now in the answers, they have considered it as a one body, as a system. Okay, who does that? Physics people probably do that. Okay, that's fine. So what I'm going to do is I'm going to treat both bodies separately so you get a different version of the answers. Okay, so we are going to resolve the bodies separately. So we're going to resolve the two bodies separately. Now, the guys who are in physics, we hope that that is the case, because basically what you're doing is you're going to look at this system which looks like this with the one system, and you've got the two masses and you're going to pull them along like that and expect that they're going to go in that direction. So just be very careful with the situations that you use in physics, okay, because it does get a little bit complicated if that is now pulled up the plane or it's over something like this shape, and we've got one mass here and we've got one there. So just be very careful if you've got bodies like that, how it goes. So just be extra careful. But if you do resolve both bodies separately, it's one method fits all. Okay? So I'm going to do it that way. Alright, so which one do you want to start with? The 1.5 or the 2? The big boss? So we're going to resolve vertically for the 2 kilogram mass. So positive is downwards, and we've got the sum of the forces equals MA, so I like to write that up somewhere because that's what we're going to use. Okay, we're going to resolve down, so 2G minus T equals the mass, which is 2, times the acceleration, which we have to work out. Okay, we're going to resolve vertically for the 1.5 kilogram mass, and therefore positive is upwards this time, so we're going to get T minus 1.5G equals the mass, which is 1.5, times the acceleration. Okay, so we have equation 1, we have equation 2. If you did it around the other way, which is the mistake, you'd have 1.5 G minus T. Okay, now, if we look at those two equations, we could just add them together, couldn't we? 1 plus 2, because the T's will cancel out. So we're going to get we'll get 2G minus the 1.5, which would be half G. So we'll just put 0.5 G. And then we're going to get equals 3.5 A. Is that correct? And therefore, A equals 0.5, because more than likely you guys will be working in decimals for this one. Should I leave it as decimals? Probably not a good idea, so we're going to put it as, that's a G. We're going to put it as 1/7 G, or G on 7. Okay, we happy with that? So let's just check that what we've got. The acceleration due to gravity is that. Find in terms of G the magnitude of the acceleration of each mass and the tension in the string. Okay, so that's our magnitude of the acceleration. Is that correct? Now, it said magnitude. Okay, if it just said the acceleration is different. So this is the meters per second squared is the magnitude of the acceleration. Now, what if the question didn't have the word magnitude in there? Find in terms of G the acceleration of each mass. How does that vary it? How does that change the question? It includes the direction. So we'd have to say, if that was the case, if the word magnitude wasn't there, we'd have to say the 2 kilogram mass is accelerating at G on 7 meters per second squared downwards, but the 1.5 kilogram mass is accelerating at G on 7 meters per second upwards, per second squared upwards. Yep. So just be aware of that word magnitude. All right, and the last thing is the tension in the string. Which equation do you like the most, 1 or 2? 1? Okay, so we're going to substitute sub A equals G on 7 in equation number 1. So we're going to get, maybe we'll rearrange it, so we get 2G minus 2A, which is G on 7, equals T. Okay, and therefore, what's our answer? T equals common denominator is 7, so 7 times 2 is 14G minus 2G, which is 12G on 7 newtons. Put a little box. You might like to say is the tension. Do we have to define the variables that we use in the question? There's a good point, isn't it? Because they haven't told us what T is, have they? Sometimes they tell you have the force P or the force F. They have T as the tension in the string. If they don't, do we have to define them? Should we say T is the tension in the string? Okay. Up for you to decide that. Well, it's pretty obvious what it is, isn't it? On my diagram. You agree? Okay. So, you know, quite often in the end, just put a word at the end and say it's the tension. Now, other thing. Should I have put tildes on the tension? Up here in the diagram, should I put tildes on the tension? Someone will say yes, someone will say no. Yeah, the magnitude of the tension is the same. Do I have to put tildes on them? Yes or no? That's a good question, isn't it? You're all stumped, aren't you? Some people say yes, they'll get it right. And some people say no and they get it right. So, alright, let's go back over it. Now, do I have arrows on my diagram? Yeah, I have arrows, don't I? So therefore, the arrow could indicate the direction of the tension, and T without a tilde is its size, isn't it? So there is a difference between T with a tilde and T. T is the magnitude, isn't it? So isn't the magnitude of the vector T? So I could label it as T tilde, but then T is its size. Yeah? So both of you are correct, it doesn't matter. But just something to bring up. Okay, if you're told to put the weight force on, maybe you should put W with a tilde under it. Something to think about. Okay. All right. Now, please don't get that question wrong when it appears in the multiple choice, if it does this year. It's not a hard question.